Okay, I think we can start now. So, good morning, everybody. So, the last scheme I started to teach last time is multi-transition MLT3. Okay, and I told you the idea here is number one, the data, the bits are in the transitions, not in the voltage level. Okay, as you will see right now. So in order to know if it is 0 or 1, you need to know if there is a transition or no transition, okay? So here, that's very easy. If you see here, number one, if the data is 0, so there is no transition, easy. If there is no transition, it is 0. So if you look at this graph here, okay, if you look here, this is positive, and then because this one is 0, I'm gonna keep it positive. This is negative, and because this is 0, I'm gonna keep it negative. Okay, so 0 does not change the voltage. If it is positive, I'm gonna keep it positive. If it is negative, I'm gonna keep it negative. Is that okay? For 1, this is for case of 0. Case of 1 is little bit complicated. Okay, in case of 1, if it is 1, so now we have 2 cases. Okay, is the voltage 0 or if it is positive or negative? Okay, so this is one case and this one case. In case of positive or negative, so I'm gonna make it 0. Okay, so if it is 1 and the voltage is positive or negative, I'm gonna bring it to 0. Okay, now if it is 0, so the voltage actually will be the opposite of the last non-zero level. What this means? It means I have to go back and see what is the voltage of the last non-zero level. If it is positive, I'm gonna make it negative. Negative, I'm gonna make it positive. Let's see here is this example. For example, if you look at this one here, okay, in this one, I told you, because this one positive or negative, this is positive, so I have to bring it to 0. Is that okay? Let's see another one. Let's see this one. Okay, this one is 0. Okay, but the voltage here, this voltage is 0. Okay, and next one, be careful because it's a little bit confusing. I'm saying the voltage is 0, and now the next one is 1. Next one is 1. Okay, in this case, because it is 0, so the voltage here has to be the opposite of the last non-zero, and this is the last non-zero here. So the last non-zero was positive, so I'm gonna make it negative, as you see. Let's see more examples. For example, here for this one here, okay. This one very easy. So if this voltage is positive or negative, and the next one is 1, so I'm gonna bring it to 0. Okay. Let's look at this one. Now this is 0, and the next one is 1. So this one has to be the opposite of the last non-zero, and this is the last non-zero is here. It is negative, I'm gonna make it positive. Is that okay? Okay. You need to think a little bit about it, but this is how, for sure, it's somehow a little bit complex, okay? Because you have to look at the last one, and it's gonna be a little bit complex. Anyway, but they found that there is something interesting here. If you have sequence of ones like 1 1 1 1 1 this way, they found if you have 1 1 1, you are gonna have a very interesting signal like this one. Let's see how it works first before. For example, here, let's start. We're assuming the beginning it is positive, so let's start from here. Okay, so this one is 1, so this one is positive, and this is 1, so it has to come to 0. I told you positive or negative, it has to go to 0. That's why this one came to 0 here. Okay, now this one is 0, and the next one is 1, so this one has to be the opposite of the last one, last non-zero. The last non-zero was positive, that's why I'm gonna bring it to negative. Is that okay? Now this one is negative, right? And next one is 1. Positive or negative, it has to go to 0. It's 0 now. Okay. So anyway, you can think about the other ones. It's almost the same thing. Okay. So what's interesting about this signal? So we can actually simulate this signal as as actually n divided by 4, which is this, like very small bandwidth. Is that okay? So anyway, I think this was the last one. Let me see if I missed something. I don't think so. This was the last one. Here I summarize everything I taught in the different schemes we have. You can see here, for in case of 2 levels, I think here up to here it was 2 levels. Okay, in the case of 2 level, as you know, the best bandwidth you can have is actually n divided by 2, right? Keep in mind, I'm gonna say it again because a little bit confusing. Please listen to me. Now, given a certain bandwidth, if I have a certain bandwidth, so I want to maximize the bit rate I'm going to get from this bandwidth. You got what I'm saying? Now I can say the same thing, but in a different way. I can say if I need a certain bit rate, okay, so I want to send this bit rate. So I have to look for the minimum bandwidth that can send this amount bit. You got what I'm saying? So here what I'm saying here, for a certain n, for a certain bit rate, what is the bandwidth you need? For sure, here minimum is better. You got what I'm saying? So you are asking the network to give you as small as possible, or as small as possible bandwidth. Okay. So anyway, so for the last one I taught, they found for this case, I told you it was n divided by 4 for this case, but for sure I'm not going to transmit 1, 1, 1 all the time. For other cases, it is n divided by 3. So we're going to keep it n divided by 3. Okay. So anyway, so you can see here, we were able to improve the bandwidth, as I taught last time, in multi-level. In case of multi-level, because you have to have more levels. Okay. By this way, when you have multiple levels, actually I can reduce the bandwidth. Or in other words, I'm keep repeating it. In other words, I can increase the bit rate given a certain bandwidth, okay, using multi-level. And this is consistent with what I told before. If you remember, in Nyquist told us, as far as I remember, there was, I think, constant, right, multiplied by n multiplied by log to L. So I don't remember how, but I think that's true. But anyway, you have log to L here. So this was Nyquist told us, if you want to increase the bit, if you want to, I think something is wrong here. Anyway, regardless, so I told it before, you can find, if you want to maximize the bandwidth, okay, if you want to increase n, I think this is B, yeah, I think this is n, okay. So now, if you want to increase the bit rate, so you have to increase L, okay. So increase the levels you have, and I told you, increasing the level may not be a practical solution all the time, because the receiver is going to be more complicated. The receiver may not be able to differentiate between the different levels, okay. Anyway, and okay, so this is the end of this part. Now I'm going to move to the next part, is block coding and scrambling. So what, okay, let me tell you what I did here and what I'm going to do in the next chapter, and what are these two new stuff I'm going to teach. Okay, so what I did here in this chapter is, this chapter is called digital transmission. Okay, as I told you before, what we are doing in this chapter is, I want to transmit digital data using digital signals. That's why you didn't see a single sine wave here. There is no single sine wave here. In next chapter, you will see a lot of sine waves, okay, because it's analog. But here, this is only digital, okay. So here we are going to transmit the data as digital, okay. So if you have a cable in this, as I said before, if you want to transmit digital signal, so you have to use the whole bandwidth. You got to, as I said before, okay. I can't do it if you give me a small bandwidth. I can do it, right? Because this one needs infinite bandwidth. Infinite. You got what I'm saying? So anyway, and then I have two different line coding schemes. And simply, what is line coding? Simply, line coding, actually, given some binary data, I have to generate a signal, a voltage, a signal, okay? And then this encoder and the decoder has to do the opposite. Given a signal, I have to extract the binary data from the signal. Is that okay? So here, number one, I explained how can you tell if this encoder is good or bad, or how the perfect encoder should look like. That's what I explained. Also, I explained different approaches from unipolar, polar, bipolar, Manchester, differential Manchester, multi-level, so there are different ideas to do that, okay? Now, that's what we call, so what we did so far, we have here line coder, okay, at the transmitter. As the receiver, I need line decoder, right? Line coder and line decoder, okay. So now I'm gonna move to the next one here, which is block coding and scrambling. So we already finished everything. You told us I have a binary data. I'm gonna convert it to digital signal. You transmit the signal. So what are these two? I don't need anything else, because I already transmitted the digital signal as digital. That's what you need, and I did it. Okay, I'm gonna tell you. Actually, these two are enhancement to line coding schemes. I can improve them, enhance it. That's it. So these are not replacement. They are not replacement to line coding schemes I explained. They are not replacement, just enhancement. Okay. That's why they are complementary to the line coding schemes. Okay. Anyway, so let's start with the first one here, which we call it block coding. Okay. So let's start with this one. Somehow interesting. So if I come here, just I want to remind you with non-return to zero inversion. Do you remember this one? How it works? Okay. I told you the way it works. In case of zero, no inversion. Is that okay? In case of one, inverted. So, okay. That's why I told you if you have sequence of ones, it's going to be invert. And as you know, this is very good when you have a lot of inversions. If you have a lot of transition, that's very good for synchronization. That's very good for DC component, for wandering, for everything. That's what I'm looking for. Okay, so this encoder was good. Even also, one of the things here, R was 1, the bandwidth was N divided by 2. So everything looks good. However, we have a problem here. What is the problem? The problem is with zeros, sequence of zeros. Okay, so if you have sequence of zeros here, based on what you see here, sequence is 0, 0, no change. That means if you have a positive value and then you have 0, 0, 0, so I'm going to keep it positive. If you have a negative value and then 0, 0, 0, I'm going to keep it negative. And as you know, keeping a voltage fixed for some time, it's bad, right? It's bad. So, okay, so this scheme looks, so everything is okay except this part, okay? Now, I came up with an idea to try to fix this part. How? Without changing the line coding. I'm going to add something to the line coding, as you will see right now. Okay, that's too simple. So your problem happens when it is 0, 0, 0. That's your problem, okay? I'm not going to send to 0, 0, 0 because that's going to create a problem. I'm not going to send. You got what I'm saying? I'm not going to send 0, 0. How you are going to do that? If your data has 0, 0, so you are going to exclude 0, 0 from the data? For sure, I can't do that, because if you exclude 0, 0 from the data, so it cannot work, because 0, 0, it's a part of the data. I have to transmit it, okay? So the way I'm going to do it, I'm going to do mapping to avoid this bad sequence. What do you mean by mapping? That's what I'm going to explain now. So I'm going to tell you the idea. For example, I want to do something, I'm going to call it 2 binary mapping to 3 binary. To 3 binary mapping. For example, this one does this just for teaching. Okay, it does not exist practically. We don't use these small ones, but just for teaching. I'm going to give you another. I'm going to give you a small scale. I'm going to teach the in a small scale, and then you're going to see it in just to teach the concept or the idea. So the idea here is that if you have, as you know, if you have 2 bits, okay. If you have 2 bits, how many options you have? I have 4 options: 0, 0, 1, 0, 0, 1, or 1, 1. Okay, so I have 4 options. Okay, that's okay. This is the bad one. So this is your data. Your data can have any one of these options, but this is the bad one. Is that okay? Okay, now if I have 3 bits, how many options you have? 8 options, right? So it can be 0, 0, 0, it can be 1, it can be 2, it can be 3, it can be 4, it can be 5, okay, it can be 6, it can be 7. So I have 7 options. Is that okay? What I'm gonna do is this is your data. Okay, I'm gonna do mapping. I'm gonna map. What do you mean by map? I mean, if I wanna transmit 1, 1, so I'm gonna actually select, for example, this one. I'm gonna transmit this one. I'm gonna select 1 because here I have 4. I have 4 codes. Here I have 8. So for every one of these, I'm gonna select 1 of these to transmit to the other side. And then, for example, 0, 1, for you, whatever, it's up to you. You can select. For example, I'm gonna take this one. Okay, and then for this one, I'm gonna take this one. So I have a fixed rule. So it's not gonna be every time I change it. So it's gonna be fixed. And now this is the important part. Now this is the bad part. 0, 0 is the bad part. Okay. Now I have a choice. I'm not gonna send to 0, 0 because it's bad. So I'm gonna, for example, select this one. So now I'm gonna take 4 codes out of the 8 here, and these 4 codes are not gonna create problem for me. Why? Because none of them are gonna have 0, 0, 0. You got the idea? So, number 1, I didn't change the line coding scheme. This is like a step before the line coding scheme. We call it block coding. Okay, block coding. So what happens here is that I want to show you here what I mean exactly. There is a picture here. What happens here is, yeah, as you see here, before I use line coding, I'm gonna use here block coding to map the bits, right? And then at the receiver side, I'm gonna do line coding, line decoding here, and then I have to return it back again. I have to do the opposite. What do you mean by do the opposite? What I mean is, let me go to my example here. What I mean, if my data is 0, 0, okay, I'm gonna send 1, 0, 1. Is that okay? As a receiver, I have to convert 1, 0, 1 to 0, 0 again. Otherwise, it's not gonna work because I have a certain data. I have to transmit exactly same data, right? But here I'm gonna just do maybe here in the middle. Any questions? So here what's gonna happen? I will try to avoid the bad sequence by having redundancy here. Okay, for sure you can tell if you want to do this conversion to actually this one is called, I think, M or NB. I'm gonna call it NB, MB. B here means binary. So I'm gonna convert N bit binary to M bit binary. Is that okay? For sure, here in this case, M has to be greater than N. Is that okay? So this number, otherwise I didn't do anything. So this number has to be greater than this number. So that I'm gonna have here more options than what I have here. And this will give me the ability to select good pattern from here. Is that okay? Any questions? Okay. That's good, right? Why? Because this line coding was a very good line coding. Everything was okay in this line coding. For example, everything was okay, except the problem of zeros. I solved it. Yes, like I solved it by introducing a new layer before I use this line coding to avoid the bad sequence, the bad patterns. Is that okay? What is the cost? Is that for free? Nothing for free, right? So if you want to get a bachelor degree, you have to put time and effort. That's how the life is. If you want to go for master, you have to, everything in life. If you want to get something, you have to pay for it. Okay. So what is the cost here? Can anybody tell? Yes. So the cost here, and instead, if I want to transmit 2 bits, I'm going to transmit 3. So actually, this is the bad side because okay. So now I'm going to increase the number of bits by 50%. Why? Because every 2 bits, I'm going to add 1 more. So that means if 1 in every 2. right? So when if so it's going to be 50%. For example, here, this one, if you multiply 1.5 or 150% of this one, give you this one. Anyway, so you are going to add more bits, and this is for sure. And this is for sure is going to reduce the bit rate, right? Because you have to add more bits here. Okay. Any questions? What is that? Yeah, it's going to introduce some delay. Okay. But here I'm more because you have to send more bits, yes. But maybe I'm not very worried about the delay here, because usually because we have other delays. The other delays usually are dominating, like you have queuing delay and other things. Usually, I think so. Anyway, but I don't think this is the main issue here. Here we worry too much, or our concern is the bit rate. So this is going to decrease the bit rate. Okay, is that okay? But this is the main point. Okay, yes, I paid the cost. However, still it's much better than the cost I paid when I solved the problem by using line coding. Because when I solved this problem using line coding, here the bit rate was n divided by 2. Is that okay? Sorry, the bandwidth was n divided by 2. Okay, but when I solved this problem, it was double. It was n. So now using the idea I have right now, I'm not going to be double. So it's going to be something in the middle. You understand what I'm saying? So still better than moving to here to solve the problem. You got what I'm saying? Because again, if you look at the idea, it's almost the same idea here, because I have to use here, I did some kind of redundancy here. I have to add one more segment L to transmit one bit. Got what I'm saying? So I did here, but the cost was too high. So here I paid too much cost by doubling the bandwidth. But as you will see right now, here I'm not going to double the bandwidth. So it's going to be something in between. For sure, I'm not going to get n divided by 2. Also, I'm not going to get n. It's going to be something in between, as you will see. Any questions? So yeah, let me go here to see. Yeah. So I just give you a toy example. When I told you it is 2B, 3B. Okay. But there is a backslash this way. We put backslash here for this one, because the reason we put backslash, because if I don't put a backslash, you will be confused with what there are several things. Maybe you are going to confuse because they're close to each other. You remember when I explained this one time, there is no backslash here. Okay, when I explained this one last time. Okay, so here this one doesn't have a backslash. Okay. But here, in order to differentiate between this one and the multi-level here, we are going to put backslash. Okay. So yeah, I think this is okay. So in general, this is a concept I taught. So in general, in my data, I'm going to substitute m bits by n bits. Maybe I said it doesn't matter m or n, but so I'm going to substitute n bits by n bits, but n must be greater than m to have redundancy, right? So to have extra pattern, so that I can exclude the pattern here and select more other patterns here. So here n has to be greater than n for sure, right? This is a practical example when you have 4B, 5B. Can anybody tell me 4B, 5B what it means? It means I'm gonna replace 5 every 4 bits. I'm gonna replace them by 5 bits. Okay, so that means you have 16 2 to the power 4, which is 16. So my data have 16 options, 16 codes, 16 cases, but the other one is gonna be 32 cases, 32 cases. Okay, one of the magic things in binary numbers is if you add only 1 bit, you double the numbers. 1 bit, you double the numbers. You got what I'm saying? So we use it in security, in cyber security, because cyber security, anyway, it's out of the scope because this is my expertise in cyber security. In crypto, we secure system using a very large space. You got what I'm saying? We increase the space. So the good thing about binary numbers, if you just increase, if you have a key, secret key, if you increase it 1 bit, you double the space. Okay, you make it more difficult to the attacker to find the key. So anyway, it's out of the scope. Anyway, So here you have 16 option, and now I'm gonna map every code here in the 16 to one code here in the 32. Okay, in the 32 options I have. In this way, I can select the good cases as I told you. Okay. Again, you should understand this is a complementary or enhancement. So I'm going to use the exact encoding scheme, and this is a layer. This is a layer, or this is a step. This is a step before encoding, and you have to decode it. You have to do the opposite of the map. Okay. Yeah, so the problem here, you are going to increase redundancy. In this case, you are going to increase it by 20%. Why it's 20%? Because every 4, so here every 4, every 5, you have one extra here in every 5. In every 4, you are going to make it 5, okay, by introducing one extra. So here you are going to increase it by 20% because the overheat is going to be 1 over 20. 1 over 5. Okay, so every 5 you have one extra. Okay, so it's going to be 20% more bandwidth here. Okay, okay. Anyway. So you can see here, it's the same idea, but I'm talking about the exact case here. For example, if you have 0, 0, I decided to select this code for it. You can see everyone here, I'm going to select a certain code. It's your choice because there is no problem. You can select whatever you want to select, but you have to. Listen to me here. Because at the receiver side, you are going to do the opposite. You are going to do the same thing, but in opposite. So that's why there is no problem. Okay, select whatever you want to select, it doesn't matter. Okay? So here I give you example to understand what I said. Yes, I'm going to be a cost, but still this cost much better than moving to Manchester, for example, because in Manchester, I'm going to be double the cost or using to any other options because it's going to be much worse than this one. Okay. Yeah. So for example, so here I'm going to give you a numerical example to understand here. So I want to send, this is the bit rate in. So I want to transmit the data 1 megabit per second using this one here. So actually, I'm not going to send. So actually, I'm not going to send 1 megabit per second, but I'm going to send 1.25 megabit per second. Okay, because of the overhead I'm going to introduce. You got what I'm saying? So, which is actually how you came up with this one. So still we have 1 megabit per second. Okay, so we still have 1 plus. Okay, the 1 extra. So the 1 extra is actually we have 4, right? So 1 out of the 4, so it's going to be 25%. Okay, so it's going to be 1 mega plus the 25% of the 1 mega. Because if every 4, I'm going to transmit 1. This one is, how can you get 1 out of 4? 25%. Okay. So 1 mega plus 25% is going to be 1.25 mega per second. So actually here you can see this is a problem. If you want to, this is the cost. If you want to transmit 1, actually I'm going to transmit 1.25 megabit per second. Is that okay? And then now, okay. So here, if you have 4, if I want to transmit 4, okay. So actually I'm going to transmit 5. How you came up with 5? So actually it's going to be 4 plus 25% from the 4. 1/4 of the 4. Is that okay? It's going to give you 5. Let's have another example. If I want to transmit 8, so 8 should be 10 here. Is that okay? So how can I get this number? So actually it's going to be 8 plus, okay, 25% of the 8, which is 2, give you 10. You got what I'm saying? So now if it's 1 mega, so it's going to be 1 mega plus 25% of the 1 mega, okay, which is this one. Okay, because every 4 is 1, it gives you 1. So if you want to know how many extra bits I'm going to transmit, so what is the relation between them? 1 over 2. Okay. So anyway, so here I'm going to transmit in this case. So in this case, this is my bit rate. This is a new N. This is the original N. Okay, so this is the original N. This is the new N. Okay, so if I want to use a non-return to 0 inversion, non-return to 0 inversion, so actually I'm gonna get any the bandwidth is N divided by 2, right? So but I'm not gonna use this one. I'm gonna use this one because if you look here, that's what I'm going to send to. So yeah, let me tell you here. So what I'm going to send here is actually is I'm going to say it in the prime, and here input here is n. So here the input here is n, the original n. This is n after you add the overhead. You can in our example, this is 1 megabit per second. This is 1.25 megabit per second. Is that okay? So here, this is what I'm going to send to do the encoder. And you know this encoder actually is going to transmit n divided by 2. Or sorry, the bandwidth is n divided by 2. So actually, in this case, I'm going to get 625 kilohertz. Is that okay? And I'm going to solve the problem we have, the synchronization problem. If I don't solve the synchronization problem, so I have to work on this one. So this is n. If I don't use the idea of the block coding here, so if I don't use it, so this is n. So actually what I'm going to transmit is going to be n divided by 2, which is equal 500 kilohertz. Is that okay? This is the bandwidth. So I increased the bandwidth from 500 to 625, and I solved the problem, the synchronization problem. This is the cost. Is that okay? So I need more bandwidth, yes. Okay, still, that's what you should understand. Still, this much better than changing the line coding and going to the other line coders that don't have the synchronization problem, like Manchester. Because in case of Manchester, actually, it's going to be n. You got what I'm saying? So if I don't use non-return to 0 inversion, so you have to go to the other ones that solve this problem, okay, as I explained to you before. But these other ones is going to be n. You understand what I'm saying? Okay, so this one with problem, this one after I fixed the problem, okay, using, and this one, if you change the line coder to another line coder, okay, that don't have the problem. Because here you have to pay double the bandwidth, which is paid. Any questions? Yeah, sure. It depends how you calculate it. I think that's wrong. I will check this one. It's, but look here. Yeah, I know. If you have, for example, 4 bits, it should be 25%. If you have 4 and then you have 1 extra, okay. So what is the ratio? If you want to get this one, how can you get this one? Actually, so it has to be 25%. I think that's a mistake. I'm gonna fix this one. I think that's a mistake. Okay, because what happened here, 1/5, or yeah, 1/5. But this is not the number of redundant bits. It's not 1/5. Okay, this is 20%. Is the ratio of redundant divided by the total, right? But if you want to get the number of redundant, okay, the number of redundant actually for every 4, 1 redundant. Every 4 is going to be 1 redundant, which is 25%. Okay, the 20%, this 20%, which I think I'm going to remove it, I'm going to change it. So actually 20%, we have 1 redundant in total of 5. So if you have some bits, so 20% of them are anyway, I don't want to confuse you. So let's stick with this 25%. Okay. If you want to get how many redundant bits, so actually it's going to be 25%. Yes. Okay. I'm gonna remove this one. Any questions? Okay. So block coding is not something. It's not a new line coder, just enhancement. Okay. So here, what you want to see here. Practically, we have another encoder. I'm going to explain quickly. There is nothing new here. For example, we can have different ideas. Like, for example, we have 8 and 10. It's the same thing. It's the same thing. So here, every 8 bits, I'm going to replace them with 10 bits. Right? Every 8, I'm going to replace them with with 10. Okay. So here, every 8, you are going to introduce 2 redundant for every 8, because they are going to be 10. So what they are telling us here, usually the way I do something like that is by using the small encoders to create a big encoder. You got what I'm saying? So I'm going to use here a small block encoder to create the big one. Okay, how? For example, if I have 5 to 6, and have 3 to 4, okay, I can use these 2 to create 8 to 10. How? If you have 8 bits here, if I have 8 bits, So I'm gonna take the fifth 5 bits. I'm gonna send them here, and then I'm gonna take 3 bits, send them here. Okay, and then this one is gonna give me 6. This one is gonna give me 4. So now total I have 10. So that's it. So I want to tell you here. If you have like encoder like this one, usually we use small encoders this way to create a big encoder. Okay, so here again, if you have 10, so I can take 5, and this one is going to convert 5 to 6, and then I'm going to take 3 bits from here. I'm going to send them to here. This one is going to convert 3 to 4. So now the output here total we have 10. Okay, sometimes we improve it more than what, okay, by having something like disparity controller. Okay, in this disparity controller, the disparity controller actually is gonna, you remember the idea of inversion when we invert it? Okay, so actually this one can invert by monitoring. So it can monitor the number of ones and number of zeros you send, and if it finds that we transmitted more ones than 0, so it's gonna invert the code. Okay, to make a balance between ones and zeros. Okay, we introduced something like I think we explained something like that before. Yeah, you remember last time when I told you about the idea of the weights, weight 0, weight 1, and so we have weight 1, and the next one is weight 1, right? So I'm gonna invert this one. It's almost the same thing here. Okay, but this is for the code. Sometimes we do something like that just to enhance it more. So again, here, very simple slide, but I want to teach here 2 things. Number 1, sometimes if I have like a big block encoder, sometimes I do it using small encoders this way. Okay, 8 bits, so 5 are gonna come here, 3 are gonna come here. Also, I can improve it more by have what we call disparity controller. So this disparity controller is gonna do inversion. It's gonna do inversion when it finds that we have more zeros. So it's gonna keep track of the excess zeros or ones. Okay, if we have more ones than zeros, so actually this one is gonna do conversion, and for sure the other side has to do the same thing. Okay, anything we do here, we have to do the opposite at the other side, because at the end, this is the data I have to receive. Okay, I just mapped the data, and then I have to map it back again. Okay? Any questions? Yes.
So as an example, 5 or 6 or 2 to 4, if I'm going to eat 80 combination, and 2 power 6, 2 4, 2 power 4, 16, 1, 80.
Now, wait a second. So this one, yeah, how many options here we have is 2 to the power of 8. 2 to the power of 8, I think 256. Okay, that's okay. Here on the other side, here, this one, the options we have from here is 2 to the power 6 plus 2 to the power 4. Right? Because we have here 4, 2 to the power 4. So 2 to the power 6. Yeah. 80, right? So 80. Total 80, right? Okay. Because here what happens, I'm not gonna convert 8 at once. You got what I'm saying? So here what's gonna happen is that I'm gonna take it, I'm gonna split it. So this 8 actually is gonna be 5 and 5 and 3. Okay, and then this 5 is gonna come here. For sure, when you convert 5 to 6, you have redundancy. You should have redundancy. No way, right? If you don't have redundancy, when you map, I have to map from a small pool to a bigger pool. There's no way you have to do it this way. Otherwise, it's not going to work, because this is the main idea, the concept here. Okay, so here, yes. So the way you thought about it, if I'm gonna map the 8, okay, as one block to, but here I'm gonna map 5, and then here I'm gonna map 3 to 4. You got what I'm saying? So you have redundancy here and you have redundancy here. You got what I'm saying? So I'm not gonna do it the way you said. Okay, the way you said, I have 8 and I'm gonna transfer 8 to 10. No, I'm not gonna do this way. what I'm gonna do, I'm gonna transfer 5 to 6 and then 3 to 4. Because I'm saying 2 pieces, and then I'm gonna combine them.
احنا اساسا لو قسمناهم 5 و 3 فاحنا اصلا قللنا الكومبينيشنز اللي مش سهله لان 2 باور 5 تيجي تو 2 2 باور 3 فهتبقى اكوردنج بس combination.
But still you have redundancy. I'm not sure. Yes, you can. Yes, I understand. But again, if this redundancy is not enough, okay, you can go to you can just. I'm not saying it has to be done this way. What I'm saying, usually, instead of creating a new encoder, I understand your point now. Instead of creating a new encoder, no, here you can create a new encoder here. If you need more redundancy, you can create a new encoder here. You get what I'm saying? But what I'm saying, instead of creating a new encoder, no, you can actually use a small encoders to implement a big one. You can, and still we have redundancy, okay? But if you need to if you need bigger redundancy, okay, you can increase it. There is no problem, or you can transfer, okay? So now I'm going to move to the last topic here, scrambling, okay? Again, same thing, similar to block coding, we call it scrambling. It's enhancement to some of the line coding here. Just enhancement. It's not a new line coding, okay? So similar to this one is actually enhancement to this one. This one is actually enhancement to this one. Is that okay? But okay, so what is the difference? Are you going to do something different here than what you did here for enhancement? The answer is yes. This one, look at the how this idea is interesting. Okay, this one has a problem. Okay, yes, this one solves the problem. Okay, I proved this one solves the problem. This one is still, it's much better than using a different line encoder. This one is still better to use this one than using another line encoder. As I give you this example is very important to understand what I'm explaining here. Yeah, this example. Oops. Yeah, this numerical example is important. Okay, so still I told you, yes, I'm gonna increase it a little bit, but it's still much better than using the other ones. That's what I did. So now scrambling is telling me, okay, now you pay the price. Yeah, still this one better. This usually what we do in network. We have a solution, I get better solution, and then I want to get a better one. Better ones is all our life we try to improve, make it better. So now I told you we improved it. Okay, now I'm going to improve it more. How you are going to improve it more? Because the problem we have right now, you have redundant bits. The bandwidth is small. You reduced the bit rate. You reduce the bit rate, or the actual bit rate. You reduced it because you are going to transmit redundant bits. The speed, right? So scrambling is trying to solve this problem. Okay. So how can I solve my original problem? When you have like fixed voltage. Okay, you have synchronization problem. These things, I want to solve it without using redundant bits. You got what I'm saying? So now, if you can do it without paying the cost, that will be great. Okay, you have to pay something for sure. I'm not gonna pay the cost by reducing the bandwidth. By reducing the bit rate, but I'm gonna pay the cost in making it more complex. You have to pay the price in any way, right? So here I pay the cost in increasing the number of bits. Here I'm gonna pay the cost in a different way. So here scrambling, I'm not gonna have redundant bits. What I'm gonna do here in scrambling, I'm gonna try to improve EMI. I'm gonna try to improve EMI. So here I'm gonna modify EMI So here it's not going to be a new layer. It's not a new layer as I did before. I'm going to do some improvement to some enhancement to MI to solve the problem we have. Let me go back to MI just to remind you of what we did in MI and what was the problem in MI. So MI, yeah, this is MI. MI was a very good scheme, as you see here. How it works, as I said before. Okay, in case of 0, it's going to be 0 voltage all the time. 0 is going to be 0 voltage. Is that okay? In case of 1, every one is going to be inverted. So the last one was positive. So this one is going to make it negative. The next one positive, negative. Okay. So if you have sequence of ones, okay, we don't have a problem. Why? Because it's going to be in positive, negative, positive, negative, positive, negative. You got what I'm saying? Because inversion. This is how it works, right? This is how it works. Every time there is a 1, so you have to go back to see what was the voltage of the last non-zero, and then here is going to be if this one is positive, and I'm going to make it negative. If it is negative, I'm going to make it positive, and so on. Is that okay? So that's okay. Sequence of ones, it's okay. We don't have any problems with sequence of 1, right? Our problem is with sequence of zeros, because sequence of zeros are going to create 0, 0, 0, 0, which is this. We don't have a problem with this component here. 0, 0, 0, we don't have a problem with this component, but we have a problem with synchronization. You understand what I'm saying? So now, so the question now is, how I, without adding more bits, how I can modify this idea so that I'm not gonna have like 0 voltage for a long time. So the way they did it here, that's what we call scrambling. So scrambling, it's going to be enhancement, okay, to the EMI scheme, okay. So, yeah, so the idea here, as you see, is every time we have 8 sequence. So here I'm gonna teach 2 ideas. They are very close to each other. So one idea we call it B8 ZS. Okay, the other idea is called HDB3. This one is used in North America. This one is used in Europe. Okay, so you will see they are very close to each other. So what this idea is telling us is, if you have 8 sequence of zeros, so in the original EMI, I have to send 0 voltage all the way, and that's bad. That's what they say. Is that okay? So now this idea is telling me, every time you have 8 zeros, I'm going to replace it with this signal here. Instead of sending 0, 0, it's going to be this signal. But also keep in mind, what about the receiver? You are only talking about the sender. What about the receiver? The receiver has to, well, this is a very critical thing. Otherwise, it's going to be random. You just change anything random. You get what I'm saying? So when the receiver receives this one, the receiver has to know this cannot be something else. This has to be 0, 0. It cannot be 1, 1, 1 or something, anything else. Otherwise, it's going to be like a miss. Okay, and that's exactly what happens. How this happens? As you see. So what is this signal here? Actually, this signal, as you see here, okay, every time there are 8 zeros, we're going to transmit 0, 3, 0 voltage. And then after that, we're going to transmit what we call V, violation. So V here stands for violation. We have B. B stands for bipolar. I'm going to tell you what is the difference between them. And then another 0, and then V, and then B. Okay? V actually is going to be always, V is going to be exactly the same voltage of the last non-zero, the same voltage. B is going to be the opposite of the last non-zero, always. Okay, so this one here is going to be the same like the last non-zero. This one is going to be the opposite of the last non-zero. Is that okay? Okay, so and that's what happened. So here what's going to happen, I'm going to send 0, 0, 0, and then here this one is going to be similar to the last non-zero. This one is going to be the opposite of this one, of the last non-zero, and then 0. And then this one is going to be similar to the last one, and this is going to be the opposite of the last non-zero. Okay, I have another example here. In this example, as you see here, So I'm going to send 0, 0, 0, and then this one is going to be similar to the last non-zero. This one is going to be opposite to the last non-zero. This one is going to be similar. This one is going to be opposite. Okay. By the way, we call this one violation because this is going to violate the rule of EMI. What do you mean? What rule? Okay. What rule is actually, and this also related how the receiver can know. This is how the receiver can know is this is not one, because the receiver may be confused and then think this is one. How the receiver can know? Because if this is a one, so this one actually has to be the opposite. That's how it works. This is the original EMI work. So it has to be this way. So once a receiver see a violation to the rule of EMI, so this cannot be one. So it has to be 0. You got what I'm saying? So again, the receiver is not going to be confused because in the original EMI, it's impossible to have two same. It's going to be two same non-zero signals this way. It's impossible to see it because if this one is 1, so this one has to be the in opposite of the last one. This is how the original EMI works. So that's why we call it violation. So here you violate. Okay. So anyway. So what's going to happen at the receiver side? When the receiver side find something like that, the receiver will understand this is 0, 0, 0, and then it's going to use it 0, 0, 0. Okay. So last one, which is almost exactly same idea, we call it actually HDB3. It's almost the same idea. So here I'm going to use 2 patterns instead of 1 pattern. I'm going to use 2 patterns. The first pattern is B00V. Okay, so here you have 2 patterns here. Just 1 second. So here I'm going to use 2 patterns. One pattern is actually 000V, as you see here. The other pattern is B00V. Every 4 bits. So this one works for 4 bits, not 8 bits. Okay. So here, every time there are four zeros, either I'm going to use this pattern or use this pattern. And always V always means a violation. So it has to be, V is going to be similar to the last non-zero. B is going to be the opposite of the last non-zero. So it's going to be the same. Okay. But the question is, when I have to use this one and when I have to use this one. You are going to use this one. You have to count how many non-zero signal you have from this between this substitution and the last substitution. For example, here we have 2 non-zero, so it's even number. So I'm going to use, in case of even number, I have to use this one. Okay, in this case, between this substitution and between this substitution, there is only 1 non-zero. So this is odd. In case of odd, I'm going to use this one, 000V. Now, between this substitution and this substitution, there is no zero non-zero signal. So anyway, so the way I have to, these two similar to what I explained before. The only difference is that you have to see how many non-zero elements between this substitution and this substitution. And based on that, you can use this one or you can use the other one. Okay. And again, nothing is new. So if you see here, once I have 4 zeros, so this one B, what B means? B means is the opposite of the last one. Okay. And then 0, 0. V, what V means? V is going to be similar to the last one. Okay. Here 0, 0. And then here this one is going to be similar to the last non-zero. And this one here is going to be opposite of the last non-zero. Right? This one is going to be similar. You got it? You understand the idea, guys? So very important thing. I fixes the problem without having redundant bits. Okay. But we have also, there is no confusion. So the receiver is not going to get confused and it's going to say, because there is no other pattern. That's the most important thing. There is no other pattern that can generate this signal. If you think that's why the receiver can know this is 0, 0, 0. Because if you think in any other pattern like 1, 0, 0, 1, 0, 0, so it's not, the receiver is not going to be confused and going to know this substitute. Anyway, so thanks. We're going to start with a new chapter next time. Okay? Oh, so this is attendance. Okay. Just give me 1 second. Uh, 9751. Don't share this code with someone outside the class.